Hey y'all, it's Sarah. I'm back with the next video in the limits portion of my Calculus 1 series, and today we are going to be talking about continuity and the intermediate value theorem, also known as the IVT. So first of all, we're just going to talk about the definition of continuity. So a function f is going to be continuous at a point x equals a if the limit of the function going to that point is equal to the value of the function at that point. So there are three implicit requirements here, right? In order for this equality to be true, both sides of the equality must exist, and then those sides must also be equal to each other. So the first thing is f of a is defined, right? F of a exists. So in order for this to be true, a must be in the domain of f. Our second requirement is that the left-hand side of the equality must exist. The limit as x approaches a of f of x exists. Now for this to be true, we need to have the left-hand limit be equal to the right-hand limit. And then our third requirement, finally, is just that the two sides of the equation, which we've already said exist, must actually be equal to each other. So those are kind of the three things that we check for when we're looking at whether a function is continuous at a point. So here's a graph of a function that has three different discontinuities, and we're going to talk about each kind. So first, here at x equals -2. Okay, we have this asymptote. From the left-hand side, the function's approaching infinity. From the right-hand side, the function's approaching infinity. So our limit exists and equals infinity. However, we don't have a value of the function actually at -2, right? It just doesn't exist at all. This is what we call an asymptote or an infinite discontinuity. Because we have an asymptote here, and f of -2 just isn't in the domain, so f of -2 does not exist. Now at 0 here, we have a point defined for f of 0, right? It's at 1. And then the limit from the left and the limit from the right are equal to the same thing, so the limit exists. However, the limit is -1, and the actual value of the function at the point is 1. Those don't equal each other, right? So this is what we're going to call a removable discontinuity. Okay, finally, at x equals 2, we have a third type of discontinuity. Here, right, f of 2 exists, it equals 0. The left limit exists, it equals 0, but the right limit is going to equal 2. And so the left limit and the right limit don't equal each other. What we have here is a jump discontinuity. The limit doesn't exist because the left and right limits are different. All right. So here's an example of how we can apply continuity. We're given a piecewise function that involves two different constants, and we want to find the values of the constants such that f of x is continuous everywhere. So there's one possible place here where this could be not continuous, right? Our first branch, we have a polynomial, that's always continuous. Our second branch, we have a constant function, that's always continuous. Our third branch, we have a polynomial, always continuous. But since we're defining, different parts of the function splitting off at x equals 0, it's possible that at x equals 0, we could have a discontinuity. We need to make sure that it's continuous at x equals 0. In order for that to happen, the limit needs to be equal to the value of the function at 0. From this branch, we're given that f of 0 equals 1. So what we need to have happen is the left limit equal to the right limit equal to 1. Now, this first branch here tells us what happens when x is less than 0. So in order for the left limit to be equal to 1, we need to have the left limit of this first branch be equal to 1. Now, Okay, plugging in 0 here, right? It's a polynomial, so we can just do that. We have 0 plus a equals 1. That just gives us a equals 1. Awesome, so there's our first condition. Now this branch is going to tell us the behavior of the right-hand limit, right? And so in order to have the right-hand limit be equal to 1, we need the right-hand limit of this branch, 3x plus b, to be equal to 1. So again, we plug in 0 here. We have 3 times 0, which is 0, plus b equals 1, so then b equals 1. So those are the constants, a equals b equals 1. Those are the constants such that f is continuous everywhere. All right, now we're going to talk about an application of continuity called the intermediate value theorem, or the IVT. So basically, we are given a continuous function. It's a function that is continuous on a closed interval. So in this graph, it's continuous from a to b, right? Between those points, this is clearly continuous. And then the other condition is that we have some value, some y value, n, right, that is sandwiched between f of a and f of b. It's either like greater than f of a and less than f of b, or the other way around. So on this graph, the way that would look is that, okay, this line here is f of a, right? And then this is b, so this line here is f of b. So we're saying that there is some value between them that we're going to call n. I'm going to say it's here, okay? So some y value, n. So f of b, f of a, n. N is sandwiched between the two, right? So if this is true, then there is some value of c between a and b such that f of c is equal to n. Now, if we look at that on the graph, okay, clearly there is a point here where the value of the function is equal to n, right? So it turns out f of c, where c is this point right here, is going to be equal to n, right? And c is between a and b. This will always be true with continuous functions, where we have some value between the value of the function at one endpoint and the value of the function at the other endpoint. Now, to see this in action, what we're going to do is consider finding x-intercepts, right, which are roots. And so there's an x-intercept whenever f of x equals 0, right? That's when a function has an x-intercept. So for this function to have an x-intercept, we can show that it has an x-intercept on the interval 0, 1 if we can find if we can find that f of 0 and f of 1 are on either side of the value 0, right? So what we want to do is plug in the first endpoint, 0, and so we have 0 to the 4th power minus 3 times 0 squared plus 1. That gives us 1. And then we're going to have f of 1. That's going to be 1 to the 4th power minus 3 times 1 squared plus 1. That's 1 minus 3 plus 1. That is going to give us negative 1. So f of 1, which is negative 1, is less than 0, is less than f of 0. So we've met our condition, right, for the intermediate value theorem. Clearly, there must exist some c between 0 and 1. So c between 0 and 1 such that f of c equals 0, which means that yes, this function is going to have an x-intercept in the interval between 0 and 1. So this is one common application of the IVT that you'll often see in calculus classes. And all you have to do is plug in points in the interval. Sometimes it'll just be the endpoints, like in this problem, but sometimes you'll have to plug in different points within the interval until you find two that are on either side of 0. And then you've proven that there must be an x-intercept or a root in the interval. All right, if you enjoyed this video, please like and subscribe. Thanks, y'all.